Hello, welcome back to CB2330, Scientific Computing for the Life Sciences. My name is Ian Hoffecker. This video is going to be about programs, how to write them, run them, reading them, and troubleshooting what's going wrong with them when that happens. So in this first video, or in the last video, we said that scientific computing is four things: modeling, numerical methods, simulation, and validation slash interpretation. And these are tasks that involve writing code in most instances. So before we can get to the core of this subject, we need to be able to program. So programming, of course, has changed a lot in the last few years due to AI tools. And you might be wondering if there's any point to learning how to program. Or if you already know how to program, you might be wondering, is there any point in maintaining that skill actively? My feeling is actually that you may in fact not need to do a lot of manual programming these days. But from a learning perspective, I think that programming is possibly one of the best ways to learn mathematical concepts and to structure your own thinking process. And if you want to become an expert in your field, you need tools for learning and not just for execution. So there's this quote from the physicist Richard Feynman: "What I cannot create, I do not understand." And this is a good mantra for us in this era when a lot of answers are plentiful, but often not completely coming from us. And that's one side. And the other is that there's increasing evidence to suggest that in programming disciplines, such as software engineering, and which I imagine is relevant to research, we see a pattern in which AI has been a partial equalizer that is narrowing the skill gap between newcomers and experts. But this applies mainly to isolated syntax tasks, and experienced users are consistently able to wield LLMs and AI tools more efficiently and safely. And these people are able to get more benefit from AI use than their inexperienced counterparts. So a student in today's world should be really concerned by this sort of rich get richer phenomenon in skill and knowledge. And in my opinion, it's important, therefore, to cultivate practices that are specifically geared toward your own sustainable self-learning practice and ability and long-term growth. So if we go to the next page here, in this video, we'll be taking a look at this program you see here. And the idea is to dissect it to become familiar with the anatomy of a program. And I hope that most of you are already at least partially familiar with the topics in this session, as we won't spend a lot of time on it. So this program is written in Python. Maybe you've been exposed to different programming languages like R or MATLAB, in which case it will be less about understanding the basic concepts of programming, which are rather universal, and more about the particular idiosyncrasies of Python, the syntax conventions, etc. And the way to understand any program is that it's a set of instructions sent to the machine, and the machine will carry out those instructions as a sequence of operations, one after another, according to what we've written here. So it starts with the first line in this case, and it ends with the last line. So on the next page here, it's interesting to step back and think about what a program is physically. So the ENIAC was one of the first generation of electronic computers ever built in 1945. And this thing had to be physically rewired. So you had something called plug boards, and programming meant physically connecting switches over days of work, days of manual labor. So the program wasn't something that you stored or wrote per se. It was really the state of the wiring of this physical machine. And this all changed in the draft of the EDVAC, the successor to the ENIAC and the next generation of computer. And during its design, the great Hungarian physicist John von Neumann, who was brought on to this project, proposed that the instructions themselves could be stored as a form of data in an internal memory system. And this is still the modern architecture, the von Neumann architecture that's used in computers today, where you have a central processing unit, the CPU, that executes the instructions. And separately, you have a memory unit where those instructions are kept along with other data. So instead of rewiring the machine every time you want to do something new, one can instead input the programs as data. And the world has never been the same since. So we type the code and the processor can't actually read it. So code goes through an interpreter or a compiler. And when it comes out, it's machine code. Machine code is structured to control a CPU. So underneath that is digital logic, ones and zeros, going into logic gates and different ones and zeros coming out of those logic gates. And a compiler will take human readable code and pre-perform a translation of that code into machine code. So Python is what's called an interpreted language, so nothing is turned into machine code ahead of time. Instead, the interpreter reads a line and does it on the fly. And the cost of this is speed. So in later sessions, we'll discuss the issues of performance and the role that programming languages play themselves. And an interesting or useful thing about this is actually we don't get errors until the line runs in the case of Python. So actually we can stop a program anywhere and inspect the state of the program. And Python is one of the best prototyping languages out there as a result of this, and it's become widely used in science. Let's take another look at this program. So what are the different components we have here? Can you spot the elements and what they're doing? So I'll list these now, and then we'll go through them in the coming slides. So jumping right in, we have a function here. We can see by the def declaration here. Down here, the for declaration here denotes a loop, and everything indented is happening inside this loop. Inside the loop, we have an example of a conditional statement or an if statement, a kind of decision fork. At the top, we have an initialization block with a bunch of variables getting defined. One of these variables is a list object, and the elements of that list are a string data type, and one of these variables is assigned an integer value. If we jump to the function, we have some docstring text here describing the purpose of that function, and we can see the parameters of that function. These are the variables that are needed, and the function is getting called later down here, and the variable count is being supplied as an argument to that function. So moving forward here, variables. So variables we can think of as labels for objects, and the blue here are all examples of variables. And in Python, you can establish a variable with this equal sign. So a variable can be used to store a number or a piece of text or a list of objects. In Python, objects have a single identity and can have multiple names. So this is a phenomenon called aliasing. So when you define a variable, you create an object, whatever is to the right of the equal sign, and you give it the label on the left of that equal sign. So an interesting error or confusion that can sometimes happen that we'll try to illustrate here is where you create an object, giving it the name, myList in this case, and you attempt to create another object with the same data as the myList object, or attempt to make a copy, let's say. But what you've actually done is you've just given an additional name to the first object. So if you modify that object, and then the change is reflected when you retrieve that object through the first name, but it's also reflected if you retrieve that object through the second name. So variable is a label, not an object. That leads us to the next topic. So what are these objects? So Python and other languages typically support multiple data types, and these are standard data structures that serve different purposes. And so some basic ones are strings. We have here, so this is text data, and a string is a sequence of characters. So it behaves like a list, and we can index it and slice it. So a nucleotide sequence, for example, in Python, can be represented with a string. So one thing to watch out for is that a number in quotes is not a number. For example, it's text. So 100 in quotes plus 100 in quotes would not give you 200. It would give you the string 100100. And this is something that could go wrong, for example, when you're reading data from a file, because everything arriving from a text file arrives as a string until you convert it. Integers are countable numbers, so they're used among other things for counting. We also have Boolean objects, so these are binary objects that have either the status true or false. And a somewhat strange fact about Python is that Boolean is a kind of integer under the hood, where true equals 1 and false equals 0. So this means you can actually add them up. If we wanted to count how many of our genes were dropouts, we could sum a list of true-false values and get a count from this. Another type of number is the floating point. So a floating point number represents real numbers with fractional parts, and it does this in a fixed budget of 64 bits. So 1 bit for the sign, and 11 for the exponent, and 52 for the digits themselves. So that budget buys us approximately 15 or 16 decimal digits of precision, and no more than that. So float is an approximation of a real number. It's not a real number. And in this statement we see here, the reason I'm highlighting this is floating point is defined whenever division occurs. So the division operator will always return a floating point in current versions of Python. So an interesting error that you can get with floating points happens when you try to compute a seemingly straightforward sum, 0.1 plus 0.2. And here we add this double equal sign, which means we're evaluating the truth of this statement. So this statement can either be true or false when it's evaluated. And if you try this, if you type this in and give it to a Python interpreter, what you'll get is false. And this is because the computer isn't storing 0.1 and 0.2. It's storing the nearest binary fraction to each of them. And 1/10 in binary is actually a repeating fraction, the same way 1/3 is a repeating in decimal. So this has to be cut off somewhere and rounded. And then the two rounding errors don't cancel out, they add to each other. And so the sum comes out as 0.3, a string of zeros, and then a 4 at the end in the last placeholder. So this is not actually equal to 0.3 exactly, and therefore the consequence is that we don't compare floats with this kind of double equal sign. We would instead have to ask if the difference between them is smaller than some tolerance level that we decide. And this turns out to be relevant for us in this course later, when we'll be computing, for example, compound probabilities or likelihoods. And often this involves multiplying hundreds or thousands of probabilities together, each of them less than a tenth, and which multiply out to 10 to the minus 1,000. So the answer doesn't come back small, it comes back as 0. So what we do instead is take the logarithm and add, since adding logs is the same as multiplying numbers, and that's why in later sessions we'll basically never see a likelihood written down, we'll see a log likelihood instead. So moving on here, we have lists. So list is a type of sequential data. It holds an object or it holds multiple objects, and it does that in order. So the genes variable is a list of strings in this case, and the counts variable is a list of integers. And order is the kind of important point here, that the list remembers that Act B came first and BRCA1 came last, and it hands them back in that order each time. So a Python list is quite permissive, actually. It will hold anything, and it can even hold a mixture of data types, and it can grow after we make it. And the way it does this is drawn here. So a Python list doesn't hold the values themselves, it holds pointers to objects that can be scattered around in memory. And the cost of that is speed and space. So lists are very flexible, but they're slow. And this is because every element is an extra hop away that needs to be routed and found in memory. And that's in contrast to a NumPy array. So this is another type of data structure that we can create in Python. And the way NumPy arrays is kind of drawn below. So when you define one, you define a contiguous block of memory holding one single type. And it's not allowed to grow, and it's not allowed to mix types. And in exchange for this constraint, it's much faster to compute on. So we start with lists because they're easy to think about, but at some point we'll probably switch to NumPy arrays because they're more performant. Now over here we have the pattern that this program is actually built on, two parallel lists. So genes and counts here are separate objects, and the only thing that's really connecting the name act B to its count here is that both happen to sit on the same position. And nothing in Python is going to enforce that. So if I insert a gene and forget about its count, then the two lists will be shifted out of phase, and the program will keep running anyway. And it would then be giving the wrong number for each gene after that shift has occurred. And so that's why we're using this zip function down here. And zip will walk the two lists in step with each other so that we never index them separately. Okay, so moving on, accessing sequential data with indexing. So once we have a list, we need to get things out of it, and we do that with these square brackets, and this is called indexing. And the first thing to say is that Python counts from 0. So the positions here are 0, 1, 2, 3, 4, 5. And this means that genes bracket 2 is not gapdh, it's TP53, the third item at index 2. So a negative index counts backward from the end. It counts the bracket minus 1 as the last element, 26. So this can be useful if you don't know how long the list is. Then this colon notation here is a slice, and this gives us a range rather than a single item. So counts bracket colon 3 means start from the beginning because the start is empty, and go until index 3. And until here means that the item at index 3 is not included. So we get 3 elements, indices 0, 1, and 2, which is 1204, 3310, and 87 here. So this is a half open interval. The length of a slice is just the stop minus the start, and two slices that share a boundary join up with no overlap and no gap. Genes bracket 3 colon is the mirror image. So you start at 3 and you go to the end because the end is empty. And the reason to be careful about all this is that these conventions, for example, in bioinformatics or other scientific disciplines, they're not necessarily consistent with one another. So some file formats may be based on inclusive or both end convention. For example, the programming language Julia indexes from 1, so one needs to always understand the convention when you're coming to a new language or a new data format. Okay, so now we have 6 genes and 6 counts, and what we want to do is perform the same operation on each one. And we could do that longhand, so we could write this classify line out for act B, and then write it again for gapdh, and then again for TP53 6 times. And that would work, but if we had a 7th gene that arrives, we would have to remember to add a 7th block. And if the operation changes, we have to change it in 6 different places and get all 6 right. And a list of genes could be, thousands of items long. So the loop is a compression of something we could potentially have written out by hand, but since it's repetitive, we'll get a benefit in the complexity of our program if we write it as a loop. So this for statement is where this happens, and everything indented underneath it is the part that is repeating. And this is a Python specific thing. So in most languages, the body of a loop is actually marked with braces or a keyword, and the indentation is just decorative. And in Python, the indentation is actually the syntax. So you'll get an error if you don't indent properly. So what's repeating here is these 4 lines, and they run once per each gene. Over here on the right, I've written out what is actually happening. So on iteration 0, gene gets this value act B, and count gets the value 1204. On iteration 1, gene is gap DH, and count is 3310. On iteration 2, gene is TP53, and count is 87, and so on down the line. So gene and count are variables like any other, and they get reassigned at the top of every pass through this loop. And here we have zip that's doing the assigning. So zip walks through the 2 lists in step and hands back 1 pair at a time. So one thing to note about this zip function is that it stops at the shorter of the 2 lists. So if we had, say, 6 genes and only 5 counts, then this loop would run 5 times and finish without producing any error, and we wouldn't hear about the 6th gene. So it protects us from misaligning the 2 lists, but it doesn't protect us from the error of making one of them too short, let's say. So if we go to the next page here, so a loop lets us do things repeatedly. A conditional lets us do different things depending on what goes into them. So it's a kind of fork in the road, and we can imagine that we can picture it as a decision tree. So the first question is here, is count equal to 0? So if yes, we go down this branch, and the answer is dropout, and then we're done. If no, we carry on to the next question. So the second question here is count less than min count. So if yes, low. If no, we've run out of questions, and everything that is left here is expressed. So we have this double equals here as opposed to the single equals from the variable side. So single equals assigns a name to an object, but a double equals asks whether these 2 things are equal, and then it gives back a Boolean answer. So it's evaluating the truth statement, true or false. And that's a link back to this data type slide. And a condition slot has to evaluate a Boolean, and the branch is taken according to whether it's true or false. And once again, the indentation here is important. So everything indented under the if is the path taken when the condition holds. And something we should be careful about is that these are checked in order, and only one of them can actually run. So elif here means otherwise try this. So it's only reached if the test above it was false. And else at the bottom is a catch-all, and this is the path that's taken when every test above it has failed. So what happens if we, for example, get the order wrong? Suppose we put count less than min count first and count equals 0 second. So EGFR has a count of 0, and 0 is less than 100, so EGFR would come back as low. And Python will not produce an error here. This is valid code. It runs. It produces an answer for every gene, and you won't get any kind of error. So if you get the order wrong in a conditional statement, it's not going to crash the program, but it will be even worse. It will be a kind of silent error. Okay, so now we put these 2 things together, and we get an interesting pattern here that's drawn on the left. And we call this an accumulator. And the shape of it has these 3 parts. So we initialize outside the loop. We perform some update inside the loop, and then we read the results after the loop has finished. So total here starts at 0, and n expressed starts at 0 before the for loop begins. And then inside the loop we have this inner conditional statement, and we add this genes count onto total, and we add 1 onto n expressed. So this line here, total equals total plus count. So this is a common construction. So it looks like an equation that is just kind of false, right? But it's not an equation. How this works is the right side is computed first using whatever is the current value, and then the result is given the name total at the end. So this is a difference between programming equals versus, say, a classical math equation. So if we kind of walk through this here, total starts at 0, act B is expressed, so total becomes 1204. Gap DH is expressed, so total becomes 4514. TP53 is low, so nothing happens. MIC is expressed, so total becomes 4926. EGFR is a dropout, nothing. BRCA1 is low, nothing. So we come out of the loop with a total at 4926 and n expressed at 3, and then we divide, which gives us this mean count of 1642. And the reason this initialization has to be outside the loop is that if we move those two lines inside it, they would reset to 0, on each pass. So we'd come out with just the last genes count instead of the sum. So this is the accumulator, and this is a useful pattern. You use this in multiple situations. So you can have a sum as an accumulator, like we have here, a count as an accumulator. You can compute a mean with a count and a sum together. So in later sessions, we'll compute log likelihoods, and this also uses an accumulator pattern as well. So this is basically what the definition of a sum is in a mathematical sense. So if you picture this capital sigma notation, it's a running total that we add to as we walk along each index. And we can start trying to think a certain way. So whenever we see a mathematical expression like this, we can ask ourselves, what is the programmatic version of this going to look like? And vice versa, what is the math equation of this block if we had to write it out as a formula? Okay, so the last big element in this program is the function. So that's this def statement up here. And the idea with a function is it's a piece of code we're going to run more than once. So we give it a name, and from then on we can call it by name instead of writing it out again. And it takes arguments, and then it returns a value. So here's the name, classify, and here in the parentheses are the parameters. The names that the function will use internally for whatever it gets handed as arguments. And count is a required parameter. So if we call classify with nothing in the parentheses, we'll get an error. Python will stop and it will tell us that something's missing. Min count here is optional because it has a default that's written in with the equal sign. So if we don't say otherwise, min count will take on the value of capital min count up here. And there's a kind of subtlety here, which is that the default is evaluated once when this def line runs, not each time the function is called. So min count is frozen to whatever capital min count was at the moment we define the function. If we go back later and reassign capital min count to 5000 and we don't rerun the def call, classify will carry on using the 100, and again there's no error. The indentation here again denotes the contents of the function, so everything indented under the def belongs to that function. And inside, count is just an ordinary variable, so it exists only while the function is running, and then it disappears when the function ends. So that's why we can use a short name like count without worrying about what else in the program might be called count. And so at the end we have a return statement, and this defines what comes back out of the function. And return does two things at once. It hands back a value and it also ends the function immediately. So the first return that gets reached is the one that wins, and nothing after that will run. A function that never reaches a return statement hands back none. So this is Python's word for nothing. And down here we have the call. So classify with count in parentheses. So count is the argument here and the actual object that's being supplied. And it gets assigned to the parameter name inside the function. And then the value that comes back gets given the name label. And that's what this conditional below then uses. So that's the whole program dissected, and now let's try to break it and explore its limits. So up here I've changed capital min count from 100 to 5,000, and of course this is completely legal to write. 5,000 is an integer. It goes into the variable. Python will run this line, no issues. And when we run this, this red block is what's called a traceback. So this is an error that was spat out by the interpreter. And the way to read these is you typically start from the bottom and then look up. So the bottom line is the error itself, zero division error, division by zero. So that's what went wrong. And above it is the trace, which tells us where. So cell line 24 here. This arrow is pointing at it, and mean count equals total divided by n expressed. So Python is telling us, correctly and precisely that n expressed was 0 when we tried to divide by it. But line 24 is not where the mistake is. Line 24 is where the consequences surfaced. And so understanding the error means tracing backwards from effect to cause. So we go backwards. N expressed must have been 0. So that means, the counter never got incremented. And this means the condition label equals expressed was never true. This means classify never returned expressed for any gene. Okay, that means every count came back below min count, which means min count must have been too big, and there we arrive on it, so on line 3. So the crash is at line 24, and the cause is at line 3, and there are 20 lines of correct code in between. This is how interpreted languages work. So the thing that we mentioned on the earlier side was that Python doesn't know anything is wrong at line 3, and it ran all these lines perfectly well until it discovered the problem when the division actually executed. So with min count at 5,000, the program crashed, and this crash gives us this information. So it stops, it points out the line, and it tells you what the problem is. But if I had set the count to, let's say, 400 instead, so then act B and gap DH and mic would still be above it, and n expressed would be 3, and the division would work fine, and we'd get a clean answer with no red text anywhere. So we'd have a kind of wrong answer, but no error to notify us. So we'll try to perform a kind of recovery test in these situations where we know the answer that we should get, and in general in this course we'll be trying to use various sanity checks to understand and catch these types of oddities happening whenever the code doesn't actually give us a specific error. So at the end of this program, we have a printed statement. And in this case, this is our kind of result or output. And the goal of the program was to compute these numbers and then report them back here. And the print function outputs a string enclosed in its parentheses. So the f prefix tells us the print function. It tells the print function that we're going to use Python's f-string format. And this is kind of smart text. So anything enclosed in these braces is live Python code that gets evaluated and then gets converted to a string as part of the message. And at the end here, we also have an optional format specifier. So this is denoted with the colon. And the 0.1f means that the number should take on a fixed format, floating point format, which is which has 1 decimal precision. And different programs can, of course, have different results. So in essentially every case, we have some kind of end result that we're interested in. And maybe that result is to obtain some number or store it as a variable, or maybe it's to produce a plot or a text file. So in conclusion, this was our quick tour through a basic Python program. So now it's your turn. So can you figure out what this program was doing now? We went through its components. Now try to put it together. So what are the inputs? What is the program trying to achieve with its output? And we haven't gone over the type of biological data that we're looking at here. And of course, this is a bit of a toy model. But if you aren't sure yet, hopefully by the end of the next couple sessions, it will be clear to you. And of course, the real way to learn this stuff is to actually dive in and start building and breaking things, making mistakes. And so in the next section, we'll discuss some practicalities and how you can get started. But for now, let's just appreciate how accessible this capability is today. So imagine you go back to the 40s and you're attempting to get something done on the ENIAC, and back then even the basic arithmetic required replumbing the electronics. So today we have this amazing capability that anyone can use, and it's this great potential for automation and systematic retrieval of knowledge and information that's right at our fingertips. So with that, see you next time.